In my defense, you said you would punch me.
What did you say?
Punch.
What you say? Like
What?
You said, what did I say? I said, in my defense.
No, what did
Blake
you
said
say?
he wanted to punch me.
Okay.
I said, good afternoon.
We learned you just ignore it. I mean,
Because I've recently got in.
I said it quietly.
Second
Uh-huh.
period, he had me like driver's ed. And I'm just sitting here like, is this
Te
every
quiero
month?
mucho, Blake.
Like, has that
not
been?
every day. It's just some days. Fine. What they need to do.
That's crazy.
I didn't expect it.
Good ass. I didn't think
They started
Shut up.
Okay, I'm sorry.
I didn't think anybody would get it.
I don't get it.
Do you want to?
No.
Yes. You want
Yes.
to? Have you seen Up? Have you seen Up?
No.
The house with the
No,
balloons, all the
Yeah.
balloons.
A little
No.
Oh, is it rough?
Nothing.
Good afternoon.
What am I talking about?
My name's Russell. Well, I'm not gonna say
Wait,
it,
how
but I
about
bet
your
you.
dog? What was the dog's name?
You can call me any name you want, but what do I look like?
He's
say
at loss.
punchable.
He's at loss.
Yeah, you look punchable.
Punchable?
Punchable.
I said a lunchable.
I'm looking like
Oh, God.
She also can do.
She can recite every word
We
to
need
you.
You need
to
to
this
do
video on YouTube and just do a laugh track.
Just
Do a laugh track. Every time we laugh.
All right, here we go. Y'all figured this out?
I'm in the process of writing.
Process.
Yes,
Okay.
sir. I'm getting there.
They were being
Better than I was yesterday.
Proceed with the process.
Proceed.
They were being a distraction.
What is after one? I meant I meant
Two.
No, what's after O? Is that a
One.
Huh?
Is that a one period?
what's after?
One minute.
Oh.
It's,
I thought it was like a per. I thought that. I
Oh,
saw
it's
the.
a period.
I
That's
saw the little
should've
dash.
put-
I didn't know if it was a percent sign or not.
Nice. These are percent.
I mean, I got you. Yeah, that's a weird percent.
I said two.
Lord.
Speaking of themselves, I went in fourth period of
Mr. Cato, what's your favorite Disney like character, like movie or like anything like
What is
kid
the first
related?
thing you see?
Star Wars is technically Disney.
Do you watch Steamboat Willie?
Good question.
Really? What? You don't know what Steamboat Willie is?
You mean the original?
Oh, yeah, I know. Yes.
I mean, I've seen it, yeah.
And you don't know what Steamboat Willie is when he goes.
The original Disney cartoon.
Oh! Did you get out of the right mind of his little old self? Makes you think that this is good. He's not that old. He's old now. Okay, so and Jacob Askew have been moved to Princeton. So they're just in there in this little.
Wait, is that not at the, that's at the beginning of Wreck-It Ralph? I remember that.
It's like at the beginning of every movie. It's like it's called Steamboat Willie. It used to be a show.
Like anybody, we put another student in there.
They can bring one.
But like, we can't just leave
They
these people
can.
alone.
I know.
They're like,
Mr. Cato, do you think it's possible that Walt Disney?
They're like they're not just friends. They're like a small gang.
yeah,
Who are these people?
two seventh graders.
It's Rachel Slocum, which is Sarah's sister, and then Jacob Askew, which you probably have no idea.
I didn't even know who that was.
He looks computer generated.
Oh my God! That's terrible.
Very true. That's a good way to describe it.
Like, have you ever seen Young John?
I love
It's like
that
Young
show.
It's like
I love
I
that
know
show.
exactly who you're talking about.
Oh,
Let's see if we can fill out the rest of this. Move on to something else. All right, so half-life is how long it takes for half of something to go away. Okay, everything has a different half-life. All right. So, for example, the decomposition of whatever A is, this has particularly a half-life of 1 minute, which is just a number I picked to be nice and easy to read. All right. So after 1 minute, how much of it's left? It has a half-life of 1 minute.
I'm gonna say 0.5.
I'm going to say 0.5 too. All right, very good. Okay.
50% remaining, 50% consumed.
Absolutely. There we go.
So smart.
Okay, now,
This is like the one right answer I've gotten in this class in the last 3 months.
good deal.
Oh.
After the next minute, how much is left?
0.25.
0.25, not 0, okay? 0.25.
You were wrong.
All right, so what happens is it cuts in half every minute, okay? 0.25, so there's 25% remaining, which means 75% has been consumed. Okay, after 3 minutes, how much do we have?
0.125.
Okay,
I love this, I understand.
Don't. Yes.
12.5%. This would be 87.5%. Okay, that's in what, 3 minutes, right? After 4 minutes, what we got?
6.7, no, 5.
But you knew it.
2.5?
Something.
Yeah.
All right, so you just keep cutting it in half, right?
Yeah.
You're so funny. You're so funny.
Turning red.
Well, yeah, there's no place.
All right, so, all right, there you go. Everybody see how that works? Okay, so a couple of ways they could ask you a question about this. They could ask you they could give you the half-life of something, okay, and say, how much of it's left after so many half-lives. They could ask you what percent is remaining after so many half-lives. They could ask you what percent has been consumed after so many half-lives. Either way, okay. One other thing to point out is that in this particular case, each half-life is the same amount of time, okay? That is only true for, write this down, for a first-order reactant, okay? So first-order reactants have congruent half-lives. Each half-life is the same amount of time. For 0 and second order, that's not the case. Each half-life is either double or half of the previous one. But for first-order kinetics, each half-life is the same amount of time. So that's one way that you can look at a table of data and possibly determine the order of a reactant. If you look at it and the half-lives are the same, if it gets cut in half in equal amounts of time, then that's a first-order reactant or some type of first-order process. They like to use radioactive decay as examples for this stuff. Radioactive decay is basically the nuclear physics version of the decomposition. So it's not much difference. It's really just no different. It works the same way. It's just an atom decaying instead of a compound decaying. All right, everybody good with that? Okay. All right. So let's get some multiple choice stuff. What we get into here.
So it's like, it's just kind of like, you know.
Well, like this ring, like it doesn't have anything. It's just.
You know, my mom doesn't use my stockings. Yeah.
No, which first?
Yeah. Can you whistle? Yes, it's all the time. I think it's for nice.
Oh, like when you just buy McDonald's chicken nuggets, but like not from McDonald's. Yeah.
All right, here we go. Answer that question right there.
I can't read it.
You can pull it up on your computer. That sign to your computer and these last multiple choice on that.
I got it.
I'm sorry,
He has a smoothie. I have a smoothie too.
I didn't mean to.
My smoothie's blue.
Wow.
Everyone's wearing cool hoodies today.
That's what I'm saying. Well, for real. I'd say mine's pretty cool.
No, that's not a hoodie, that's a sweater.
It's big.
That's a sweater.
We haven't talked about mechanisms yet, have we? I knew there was something else I was supposed to talk about before we started this. Okay. All right. Sort of a timeout then. Hang on. All right. Let me think you just a minute.
Yes, I get it. Including.
What?
Well, it's still in the second one.
Hoodie? Oh.
What?
What? What? What are you talking about?
Stop.
Whoa. That's a cute butterfly.
Sometimes I forget I'm an
Okay,
Like, I
go.
don't know an ACT. Like, what is that? Did y'all finish that essay?
But I also wrote the same essay. Only took the controversial essay. That was my topic, was technology.
Oh.
Yes. Because I don't want to. I don't see why you have to.
What in the world? Like,
Has your regular chemistry like smacked those like the metal things together? You had the spark. Like those two.
No, we'll get to that probably in the next couple of days.
Can we do that again?
Yeah, can you re-explain that?
Just sit.
Sure, I'll have them out in a couple of days.
Yay!
I wasn't here for that.
Really?
Yeah, I wasn't.
I was
here
at the
for, like,
STEM
He
camp.
let us do it.
I don't remember where I was.
I think the 2 minute long. And it makes a spark.
I don't know.
Really?
I definitely did it.
I remember
I
Hayden.
just
You
don't
miss,
remember.
you miss Hayden.
Just silent.
There we go. Now it's
Toys.
Go.
No, I have to
Girl.
say, he's one of those people that talks to talk. He talks to fill the silence. He talks to
Yes, every day, like I'll be like zoned down and go, dude. I'm like, what's up, dude?
He doesn't talk to me anymore.
Hmm?
He doesn't talk to me anymore.
Maybe it's because you rejected him.
That's true.
If it would take the hit, it would be a problem.
Can't take it.
I tried. I'm too nice.
Question, Tatum. So say, well, clearly this is not a realistic situation. But if you're in high school and like a girl had asked you to go to like an Auburn, like what are you an Alabama Auburn fan? Or are you what college fan are you?
Jack State.
If you, but okay, yeah.
Let's go.
They asked you to an Auburn game for free. Would you go? Even though if you knew she liked you, but you didn't feel like, would you still go? If he was free.
Yeah, I was. That's probably what happened.
I'm getting a free ticket. I got a lunch.
Yeah.
That's just not me.
Sydney, like, I mean,
I mean, it would
she
depend, it would depend on who it was.
He was hating, like, no.
It would depend on who it was.
He's too nice of a person, and I'm too nice to be.
What?
Like,
What are you talking about?
Huh?
Too nice.
Are you talking about
Jack
hate?
Dan.
Yes, I did, but
Oh, wait,
I
wait,
didn't
wait, what are we
go.
talking about? Oh,
Oh,
still?
that's our problem.
That's still a thing?
No, it was never a thing.
But you guys.
No, I mean, like.
Yeah, going on 4 years now.
4 years he's been bothering you?
No, they were
No, he
saying,
doesn't.
they were saying, well, y'all were a thing. I was like, yeah, they going on 4 years now.
When's the wedding?
Everyone gets my name when they find out about it for like.
I don't know, when
He's
he's
at tumor school.
I don't know, when he's
Yeah.
Ozone.
frozen.
No, that's ozone.
I know, but I'm frozen. I love
You good?
Are you good? Following directions. I'll teach you later.
What?
Oh my god! Why did he say? Who we? Is that Blake?
I love when I go to class, all the
Like the like chicken and pig.
No.
me, you, and Brayden, and Vicky.
I need to put one of those.
I never see any of your.
Wait a minute.
I always see yours.
I see Sydney's occasionally, I always see Blake's and I always see Nick's.
That one about, you know, I did erase it, sorry.
It's okay.
I always see.
What you see?
You the guy.
I really like writing.
I know.
Hey man.
I've seen a bunch of them.
Oh well, actually, I
I
looked up in a rainbow.
I gotta listen to this just a second. Yeah, go say.
Sorry, you did not do anything this far. So we should have shown. We should have shown.
What did she say? I don't understand. I don't understand. That's just how you sounds like a man. I couldn't be in the same room as all of them. I'd literally be on the floor. I can't breathe. Like,
No. Oh, baby. I'm
They're all gone.
Why?
They gotta have houses.
Dude.
What?
I wanted to come see the puppy.
Bro, there was
I
no
was
time.
gonna say-
We were really busy all the
There, you
time.
got puppies?
We had puppies.
Oh, what kind?
Shiloh Shepherds.
What is a Shiloh
It's like a bigger, more friendly German Shepherd.
More friendly, yeah, sure.
Unless
That one
I
tries
mean,
to.
they're like,
Yes,
yes,
Daddy.
Arbor trust.
it don't bite.
Like, no, they don't bite.
And if your dog's named Sweetie or Princess, it's
Like,
literally
be
like,
for real.
I think they're
They're just starting.
Like, too.
Well, it wasn't like that was a decision. That was just always the plan.
Yes.
Lake Massacre, I was checking out.
Where are you going?
Later, Russell.
Okay.
Where are you going?
Where are you going?
What
do you mean you don't know?
Say something.
Nobody checks out into the 11th grade and doesn't know why.
That's a fact. That's a fact. That's a fact. Last time I
No, if not me, you have a fatal explanation. Because now you're not learning chemistry and you're gonna be behind.
I have the video.
Oh,
we didn't. Girl, the video was full of us chat.
I completely
If
forgot
you
about
guys,
the video.
You're trying not to. I don't think they meant to say Blake though, right?
I'm not telling you so.
Blake.
It's okay, you don't need to.
You don't have to do it.
Blake, what's your middle name?
Blake.
Blake.
Oh, yeah.
Oh, Russell Blake. What's your first name?
Jeffrey.
Really?
So why is it
Is Jeffrey Blake Lorenzo Mansfield?
Oh, yeah, we've been over this.
Oh.
You just gave him my full.
Government
I
name.
Identity.
Give them your address.
It's on video. It's on video. Go back and
Do you not get social security number? Go ahead.
Go ahead and say
that.
452.
I'm gonna say your birthday.
Oh my
I'm
gosh!
gonna tell them your birthday. I'm gonna tell them your zip code. I'm gonna tell them your address.
I bet their zip code's real hard.
Yeah, the zip code's really fine.
Yeah.
The people in the world don't know that. I just imagine like one day, maybe like the last remains of humanity will be like a hard drive containing the tapes of this class.
That would be funny. It's like here from like 1,500 years ago. We have these strange.
We know Russell Jeffrey Blake. Like the history books are gonna think your name was actually Russell.
Struggling.
All right, here we go.
It's not working.
Make
You gotta
another
go.
All right, so here's what a mechanism is, okay? It's the step-by-step process in which a chemical reaction actually happens. These are called elementary steps, okay? So let's read this. The following reaction, 2 nitrogen dioxides plus fluorine makes 2 of those things, okay? That's the following rate law. Okay, so it's apparently first order in nitrogen dioxide and first order in fluorine. You know that because there's understood ones right there, right? Okay. And following proposed mechanism. Now, one thing about mechanisms is none of them are provable. So the chemists come up with these proposed mechanisms, all right? What you'll be asked to do is a couple of things. Well, the first thing you'll be asked to do is be able to determine if a proposed mechanism is valid. Okay, so this is a proposed mechanism to say that what happens here is step 1 happens and then step 2 happens. So an NO2 molecule and a fluorine molecule react together, and that produces an NO2F and a single fluorine atom. And then that single fluorine atom reacts with the other NO2 molecule to make the other NO2F that's supposed to be produced. Okay? 3 molecules, 2 NO2s and 1 fluorine, simultaneously hitting each other with correct energy and orientation is almost statistically impossible. So anytime you have more than 2 stoichiometric coefficients, like a 2 and a 1, anything adds up to be more than 2 on the reactant side, it's got to be a multi-step process. Okay? There's 2 ways that you check to see if this is correct or not. Okay? One is it has to add up to be the overall reaction. Okay? So you've got to be able to add these 2 elementary steps. These are called elementary steps. In this case, there's 2 of them. There might be 5, or there might be 10, or there might be 50. Who knows? But in our case, for what we'll see, there'll be 2 or maybe 3. Okay. But those 2 elementary steps have to add to be the overall reaction, because if these parts don't add to be the whole, then it's obviously wrong. Okay. So to add reactions together, it's like algebra class. I'm sure we've done this before. Okay. You add what's on the same side and cancel what's on the opposite side, right? So these single fluorine atoms would cancel out. And that leaves me with 2 NO2s and an F2 producing 2 NO2F, which is what the balanced equation is, right? So it passed test number 1. Okay. Oh, I got to tell you one more piece of information. There's always one step that's slower than the rest of them. Okay? That slow step is called the rate determining step. We'll graph that out here in just a minute. See what that looks like on an energy graph. Just a second. The second test that you're going to run on a mechanism to see if it's correct is the coefficients of the slow step plus any step above that will equal the orders of the reactants. Let me show you what that means, okay? This is the slow step, the first step, according to this proposed mechanism. The first step is the slowest. There's no step before that, okay? That means that what they're saying is this has to match up. These ones right here have to match the orders of the reactant, and they do, okay? So it passes that test, okay? Now, what is the rate determining step? Well, if we drew an energy diagram of this, like we normally would, okay, and let's just, I don't know, let's see what this is. This is probably exothermic, let's go with that, okay? We would draw a curve like this, right? And over here, there would be two NO2s and a fluorine. Down here, there would be two NO2Fs, right? And there's our activation energy. That's a simple reaction diagram. But that diagram assumes that this happens in one step, and it doesn't. So what this actually should look like is this, because there's two steps, okay? So we should start here with a nitrogen oxide and a fluorine. And what do we call this at the top of the hill right there? The what?
It's also the keyword.
Activated complex?
Yeah.
Okay, there we go. Or transition state, either one, all right? So what's going to happen right there is we're going to get, we're going to get some kind of a, well, I'm going to try to do that. Let's just put down here. We're going to get an NO2F and a fluorine, and then we'll get another transition state here that leaves us with two NO2Fs. Okay. There we go. That works. Now there's actually three things there. Okay. All right. So you've been on a roller coaster before, right?
Oh, yeah.
Okay. Once you get to the top of the highest hill, right, it just turns you loose, and you get over all the other hills without having any extra outside intervention, right? Did I follow that? Okay. So rate determining step is the one with the highest activation energy. Okay. So meaning that once you get to the top of this, once you have enough energy to get here, then everything else happens. You got plenty enough energy to do everything else. Okay. Same concept as a roller coaster. All right, notice that we canceled something out over here when we added these up, okay? So there's two things that occur in these mechanisms that will cancel when you add the elementary steps together. One is called an intermediate. That's what this fluorine atom is right here, okay? So intermediates appear, then disappear. So in this particular process, the fluorine atom appeared, it was a product in an early step, and then it disappeared. It was a reactant in a later step, causing them to cancel out because they're on opposite sides. If you flip that around, it's a catalyst. So a catalyst will show up in a mechanism because it disappears, then reappears. So if you have a mechanism, you can add the parts together, which you cancel out, and just look at the things that you cancel. All right, if it was a reactant and it comes back as a product at the end, it was a catalyst. If it's a product and then it's later on a reactant, so it doesn't end up, neither one of these end up in the overall reaction, and it's called an intermediate. It's an intermediate product, okay, which then is later on consumed and doesn't show up in the overall equation. All right, so there's a quick overview of mechanisms. Let's see if that helps us with this question. When the concentration of substance B in the reaction above is doubled, all other factors being held constant, it is found that the rate of the reaction remains unchanged. What does that tell us about substance B? Zero order, okay? The most probable explanation for this observation is what, okay? All right, well, if it's not in the rate law, then it's not going to be part of the rate determining step, okay? It's involved in something that happens after that. So what answer is that? Let's see. So it's not A, right? It says order is 1. We said it was 0, okay? The substance is not involved in any steps of the mechanism. It's got to be part of at least one step somewhere, okay? Part C says substance B is not involved in the rate determining step of the mechanism, but is involved in subsequent steps. That would be the right answer. That means it's not in the rate law, then it's not part of the slow step of the mechanism, okay? Which means it's not part of the rate determining step. All right, it says D, why is it wrong? Substance B is probably a catalyst. No, it wouldn't show up. Catalysts don't show up in the balanced equation. It's not a catalyst, it's a reactant. The reactants are products, and then there's catalysts. Okay, that's a separate thing. Part E, or answer E, the reactant with the smallest coefficient in the balanced equation generally has little or no effect on the rate of the reaction. That's just a false statement. Okay, looking at the coefficients in the overall balanced equation doesn't tell you anything about the orders of the reactants. Okay. If you look at the coefficients in elementary steps, they tell you about the orders of the reactants. But in the overall balanced equation, you can't judge reactant order by coefficients. They don't have anything to do with each other. Because reactants have to be in the mechanism. It would be part of the reaction. It's got to be in the process. The mechanism is just a step-by-step process that this happens. B has to be in it. All right. I think now we discussed everything. We can discuss and try to answer the rest of these. Let's see. All right, y'all look at that one for a few minutes. There's 4 or 5 choices. Just scroll up. Get them all on the page.
If you hit the 3 dots in the top right, you can zoom. Choose zoom percent. You can hit the minus. Zoom in a little bit.
Like that.
Yeah.
There we go. What type of rate law process are we working with here? Differential or integrated? Y'all are mumbling stuff. Which one is it? Integrated. Integrated rate log. We have time and concentration, and then they took the natural log of concentration and the inverse of concentration, right? That's the integrated system, okay? All right, so according to that chemical equation, a sample of N2O5 was placed in an evacuated container and reaction represented above occurred. The value of the pressure of N2O5, the partial pressure of N2O5 was measured during the reaction and recorded in the table below. Which of the following correctly describes the reaction? So we don't know if it's first order, second order, zero order, whatever, right? So how do you determine that from integrated rate laws? Do what? Which one makes a straight line, right? Now, we obviously do not have time to sit here and graph this stuff, correct? You got a minute and a half to answer the question, right? So how do you determine a linear relationship just by looking at a data table? No. So y'all were given these data tables in algebra class starting in like the 7th or 8th grade, right? You know, they said graph it. Always come out to be a perfect straight line. No. 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 Just by looking at the numbers. If it's going to be linear, then the gap between the numbers has to be consistent. Okay? So if you look at time, right? What's the difference in every one of those numbers? 100, right? Okay. If you look at pressure, the second group, what's the difference in 150 and 75? 75. What about 75 and 38? Not 75, right? Okay, so that's not, so a graph of pressure versus time is not going to be linear. See that? Follow me? All right, look at natural log. What's the difference in 5 and 4.3? 0.7. What's the difference in 4.3 and 3.6? 0.7. What's the difference in 3.6 and 2.9? 0.7. So a graph of time and natural log of pressure right there is going to be linear. Because the time increments are the same and the natural log increments are the same. Everybody follow that? If you made a graph of those two things, it's going to be a straight line. Just for the fun of it, look at the inverse. It's kind of hard to do that math there. But anyway, 0.06, well, it's not too bad. 0.0067 to 0.013, that's like 0.067. But then the next one is 0.14, and the next one is 0.28, and so on. So they're not the same, right? So the linear relationship will come from time versus natural log. So that makes N2O5 be a what order reactant? First. Very good.
Because they're directly proportional.
Yes. No. No. Because they're linear. That's two different things.
Okay.
The relationship between time and the natural log of pressure is linear. Which is sort of kind of the same thing. But the directly proportional is more to do with would be the pressure and the rate itself. All right, so what's the answer? B. Very good. How much time do we have?
4 more.
4 minutes. Let's try to do one more. Okay. Possible mechanism for the overall reaction represented above is the following. That's two. They're giving you 2 elementary steps. The slow one is the first one, right? It says there. It doesn't have to always be the first one, but it is here. Okay. Which of the following rate expressions agrees best with this possible mechanism? Well, the coefficients in the rate determining step should be the orders of the reactant, right? So first off, is there any oxygen in the slow step of the mechanism? No, so that means oxygen is what order?
0.
0. Very good, 0. How many nitrogen monoxides are in the first step? 2. So that means NO is what order? Second. Okay. So this is second order in nitrogen monoxide and 0 order in oxygen, which would be that rate law right there. Okay.
Is it just second order because there's 2 of them?
Second order because there's 2 of them in the rate determining step of the mechanism.
Oh.
Yeah. Pop quiz. What's anything raised to the 0 power equal?
1.
1. Very good. Okay. Make sure we know that. All right. We'll stop right there because the bell's going to ring before we do another one. We'll pick back up here tomorrow.
No, that was.
Mr. Gator, can you go back to the last question?
The last question.
Like, number 2? It's the only reason we looked at the, time and the natural log is like, because they were like the same in difference. Like, why wouldn't the
We're trying to
other
figure
two
out which
matter?
one. So if we were doing this all the way out, if this was like a long pre-response problem, right? If we were doing this for homework, we would make 3 graphs, right? Graph pressure versus time, natural log of pressure versus time, versus pressure versus time, right? And one of those is going to be a straight line.
The natural log, okay.
That one is 0 order because that one is first, that one is second. So there's a shortcut to all that. You've got all these numbers over here. These are all evenly incremented, right? 100, 100, 100. So which one of these is also equally incremented? It's that one.
So that one was.
So the graph, if you went to the trouble of doing all these graphs, you're going to get a curve, straight line, a curve.
I was confused for a second because I didn't realize that they were all with the mix.
Yeah.
Mr. Cato.
See ya.
Yeah, I was like,
Like with the graph into the box, I thought it was like its own like
Yeah.
instead of them all having. I didn't know. Say, look at AP Kim on the board.
Fourth period.
What is that?